Let's now focus on the BMS algorithm. This part of the battery management system monitors, protects, limits, and reports measurements from the battery pack. The subsystem on the left uses individual cell voltages and temperatures to calculate maximum allowable charge and discharge current levels. When a cell is at low SOC, its voltage is low, and it is important to prevent the cell from delivering a large amount of current, since this would cause an excessively large voltage drop that could potentially be below the cutoff voltage specified by the cell manufacturer. Comparing the minimum cell voltage in the module against this lower threshold and dividing it by the maximum internal resistance value calculated for this cell, we can compute a voltage-based current threshold. We also know that it is important to limit current delivery or intake when temperature is too high or too low. Using a lookup table with a rising or falling S-shaped profile, we can specify a current threshold based on temperature and modulate the allowable current delivery. This is very important to avoid physical damage to the cell materials at high temperatures, both during charge and discharge, and at low temperatures during charge, since doing so below freezing temperature is not allowed. These two thresholds are then compared against one another, and the lowest becomes the current limit. The subsystem labeled state machine defines the main operating state of the BMS. It is represented here using state flow, a Simulink add-on toolbox meant for designing state logic. In state flow, we use components representing states that are active or inactive depending on the conditions. And the text we write inside the state is code that executes on entry, during, or an exit from the state. The state machine has 4 parallel states. Parallel here, meaning that they can be active at the same time. The first one defines the variable BMS state, which indicates standby, driving, charging, and fault. Charging comprises constant current and constant voltage stages. The second state switches the fault state on in case of a current, voltage, or temperature value reaches an unsafe level. The third and fourth states define the contactor on and off switching sequence for the charger and inverter. This is needed to avoid an excessively large current inrush at the beginning of the charging stage.